Hello everyone, welcome back. I'm here again with one more video on P block elements. And today we will be talking about group 16 elements. And in group 16 element, we will be specifically studying the oxygen and its compounds. So let us go ahead with first the two allotropic forms of oxygen, that is dioxygen and the trioxygen, which is commonly known as ozone. And then we'll try to understand the oxides in detail. So first, let us start with dioxygen. So the main preparation of dioxygen, or the laboratory preparation of dioxygen, is done by the thermal decomposition of potassium chlorate. Okay, so that's the reaction. We take potassium chlorate, okay, we heat it at nearly to 420 Kelvin in the presence of a catalyst, which is manganese dioxide. Okay, it gives the potassium chloride and oxygen. And remember that this reaction requires the presence of this particular MnO2 because the thermal decomposition or the decomposition temperature of potassium chlorate is quite high. It is nearly to 672 to 720 Kelvin. Okay. So in presence of MnO2, what it does, it lowers the temperature for the decomposition of KClO3. Okay. So it nearly takes place at 420 Kelvin instead of 672 to 720 Kelvin. Okay, that's why the reaction is carried out in presence of MnO2. Dioxygen can be prepared in various other ways also, like we can heat it actually by heating dioxides, by heating peroxides or some higher oxides, okay, like silver oxide. Okay, if you heat it, it will give you silver and oxygen very easily. Manganese dioxide, okay, it will give you trimanganic tetraoxide. You can see Mn3O4 and oxygen. You can take barium peroxide, okay, heat it, it will give you barium oxide and oxygen. Okay, so these are the various ways which you can get oxygen from different oxides or peroxides or higher oxides. Okay, so these are the two main preparation of oxygen. Now coming for the properties of oxygen. Okay, reaction with metals. As we know that whenever oxygen reacts with any element, it usually forms oxide. So obviously with metal also it will easily form oxide. Okay, active metals like sodium and calcium reacts at room temperature, okay, to their respective oxides. So like sodium will go for sodium oxide and Na2O, calcium will go for calcium oxide. Okay, it reacts with the metal like iron or aluminium or copper, but remember that at high temperature. Like aluminium, when it reacts with oxygen, it will give you aluminium trioxide or aluminium oxide. Iron will give you iron oxide. Okay, it reacts with non-metal as well as with non-metals, and it will give you oxide again. Like carbon, it reacts to give you carbon dioxide. Phosphorus, it reacts to give you phosphorus pentaoxide. Okay, it reacts with compounds also, not only with the elemental elements or elemental state, but with compounds also. Okay, like it reacts with hydrocarbons. One of the example, which is methane, it reacts with methane to give you carbon dioxide and water. Not only methane, but any hydrocarbon, whenever it reacts with excess of oxygen, always give you carbon dioxide and water. It reacts with compounds such as HCl also. Okay, it easily reacts with HCl in presence of oxygen, in presence of those catalysts like 700 Kelvin and CuCl2, okay, to give you H2O and chlorine gas. This particular second reaction is nothing but the Dioxygen process for manufacture of chlorine. Okay, so these are the various examples through which we can see that how oxygen reacts with various metals, non-metals, and compounds. And in every cases, what it is giving is oxides. Okay. Then what is the use of dioxygen? Okay. It is actually used in oxyhydrogen and oxyacetylene torches, okay, which are used for welding and cutting of metals. It is a good oxidizing and bleaching agent. Okay. It is liquid oxygen is commonly used as a rocket fuel. Okay, the rocket fuel which we use is a mixture of liquid oxygen and liquid hydrogen. Okay, so liquid oxygen is actually used as a rocket fuel. Okay, it is also used in removing the impurities in the metallurgical process. Okay, through roasting and calcinations, we remove the particularly through roasting, we remove the impurities. Okay, so that is how actually oxygen is used, okay, in various applications. Then coming for the second allotrope of oxygen, okay, that is ozone. Now, as we know that this particular molecule, okay, this particular substance is protecting our earth from the harmful UV radiations. Okay, it is present in stratosphere. Okay, and it absorbs the harmful UV radiations. Okay, and decompose itself into O2 and atomic oxygen, where O2 and atomic oxygen again combines back to give you O3. That is how actually that cycle of ozone layer goes on, and the UV light in that process get absorbed. Okay, and remember that ozone being a very endothermic compound, okay, it absorbs heat and decomposes very easily. That's why it absorbs the UV radiation very easily in the stratosphere and decompose itself to give you molecular oxygen and nascent oxygen. Okay, so that is how actually it help us to prevent the UV radiation to come into the earth surface. Okay, so preparation, how do we prepare it? What we are talking about is laboratory preparation. So there is a specific preparation for ozone, and we need an apparatus which we called as ozonizer. Okay, ozone is prepared by passing silent electric discharge. Okay, I'll be coming into it. What is silent electric discharge? Through pure, cold, and dry dioxygen. Okay, so you have to take oxygen. So our starting material is oxygen, and we pass actually a silent electric discharge through it, and the apparatus which is actually done or which is used in the process to pass the silent electric discharge is nothing but known as ozonizer. Okay, so this is the reaction. It's a reversible reaction, very important. Okay, that 3O2 takes actually the silent electric discharge. When you pass silent electric discharge, it gives you O3. And very important that this reaction is actually absorbing and nearly takes an energy of plus 142 kilojoule per mole. It's an endothermic reaction, very important to understand that. Okay, so positive enthalpy change, that means obviously this is a endothermic reaction. So now very important, okay, try to understand this. As I have already told you that ozone is an endothermic compound also. It decomposes very easily when you heat it or give a high amount of energy, or basically when you heat it. Okay, whenever you heat ozone at high temperature, it easily decomposes to give you back to oxygen. Okay, so that's why this reaction is reversible. But try to understand, when you prepare ozone from oxygen, it requires energy. Okay, so O2 to convert into O3 requires energy. And if that energy is given in the form of heat, then that heat will again convert O3 back to O2. Usually in this reaction, only 10% conversion of O2 to O3 takes place. Okay, not much. Okay, only 10% of conversion actually takes place from O2 to O3. Okay, and the product which you get is sometimes known as ozonized oxygen also. Okay, and that's why actually you need that heat. But remember that you cannot give that heat in the form of heat itself, okay, or the energy which is required, okay, plus 142 kilojoule per mole, you cannot give in the form of heat, because if you give in the form of heat, then the heat which is generated in the system, okay, which is given to the system, might convert actually the ozone back to oxygen. So that's why we give an electric discharge, but a silent electric discharge. By silent electric discharge, what do we mean over here is the sparkless electric discharge. So we are giving an electric discharge without any spark. Okay, sparkless. So silent over here, what it means is sparkless electric discharge. Okay, so whenever anyone actually mention the silent electric discharge, what they basically mean is sparkless electric discharge. Okay, so basically we don't want to convert O3 to back to O2. That's why we need silent electric discharge. Okay, the formation of ozone from oxygen is an endothermic reaction, as you can see. Therefore, it is important to use, that's what I've told you, a silent electric discharge in its preparation to prevent its decomposition. So if you use a spark electric discharge, let's say electric discharge which is generating spark, then that heat which is generated will convert ozone to oxygen back. So that's why we need a sparkless electric discharge. Okay, and that's why we need a specially designed instrument which we called as ozonizer. Okay, so that particular condition is very important to prepare oxygen to ozone. Okay, and remember that the conversion percentage is very, very less. It's almost to 10%. Okay, so only 10% of the oxygen is converted to ozone. So that is how actually we prepare ozone from oxygen. Okay, now coming for the properties. Okay, it has few very important properties, and one of the property which it is very much used for is the oxidizing agent. Okay, ozone is is one of the most powerful oxidizing agent. And why it is so, just now what I have told you, because by absorption of heat, it's an endothermic compound. So whenever it absorbs heat, it decomposes very easily to give you O2 and nascent oxygen. And nascent oxygen being very reactive, it's basically atomic oxygen. So being very reactive, reacts with any other system. Okay, as a result, get actually or oxidize the other systems very easily, whether it is any other element or compound. Okay, that's why it acts as a very powerful oxidizing agent. Okay, like for example, if you take lead sulfide, okay, PBS, and react it with ozone, so what it will convert into is lead sulfate. See, clearly you can see, okay, 4 oxygen is being added from lead sulfide to lead sulfate. And obviously what you are getting is oxygen, that is the side product of the oxidation reaction of ozone. Like this also, potassium iodide in presence of water, and when you pass ozone, what you get is potassium hydroxide and iodine. So basically over here, iodide, okay, I minus is getting oxidized to I2. Okay, and this particular reaction is quite important also. This particular reaction is used to quantitatively estimate ozone also. Okay, so this reaction, if you carry out in the presence of excess of or if you take potassium iodide, okay, excess of potassium iodide when you react with ozone, okay, in presence of a borate buffer, okay, then iodine is released. Okay, this iodine which is liberated, if we titrate it against sodium thiosulfate, then how much of the ozone is liberated can be easily quantitatively estimated. Okay, so that is how actually this particular reaction is used for quantitative estimation of ozone also. Then coming for the bleaching agent. Okay, so remember that any oxidizing or reducing agent always act as a bleaching agent, because an oxidizing agent always liberates nascent oxygen, a reducing agent always liberates nascent hydrogen, and since the being very reactive, reacts with any coloring matter, okay, any organic colored matter to make it colorless. That is what we call as bleaching action. Okay, it is used as a sterilizing agent also, since it actually gives that nascent oxygen, so it reacts with various pathogens, bacteria, viruses, and or any organic matter, okay, in fruits, vegetables, and basically kills it. Okay, so that's why it is used as a sterilizing agents also. So it acts as a bleaching agent for vegetable coloring material. See, if you take organic coloring material and react with ozone, okay, it gives you, obviously it oxidizes it, and that coloring matter becomes colorless, okay, and giving you side product as oxygen. So that is what we mean by bleaching agent. So in general, all oxidizing and reducing agent act as bleaching agent. Okay, but it may happen that some may be permanent bleaching agent, some may not be. Okay, temporary, some may be temporary bleaching agent. Okay, so that depends. Then coming for the structure of ozone. Okay, ozone is a bent shape molecule, or what we call as angular, which you can see in the screen also. Okay, so it has a bent shape. It is not a linear molecule. The particular lone pair which you can see on the screen, okay, that lone pair bond pair repulsion makes the angle. Now, and if you see the geometry of the electron pair, basically it is a trigonal planar, but because of the more lone pair bond pair repulsion, this particular angle which you have, it's not nearly to 120 degree, it is less than 120 degree and comes to nearly 117 degree, 117 degree. Okay, so this particular molecule is bent shape. And remember that not only that, if you can see the structure over there, one is double bond and another one is single bond. Okay, now obviously we know that double bond are shorter than the single bond, but in ozone, very interestingly, that these two bonds are equal. Okay, they are not, one is not longer and another one is not shorter, both are equal. And why it is equal? Because it undergoes resonance. Okay, because of resonance, the bond is neither a single bond nor a double bond. Okay, it acquires a partial double bond character. So you can clearly see in one resonating form or canonical structure, you can see over here there is a double bond. In the same case, in the another structure, there is a single bond. Here it is a single bond, in another case it will be a double bond. Obviously, because of resonance, there is a delocalization of the electron, as a result of which what will happen is the bond length of the two system becomes same. Okay, so that is why actually in ozone the two bond lengths are same, even though one is double and another one is single, and that is because of resonance. Okay, now coming for the next, that is use of ozone. Where do we use ozone? Okay, it is used for disinfecting water for drinking purposes. Okay, and because ozone has germicidal properties, that's what I've told you. Okay, it's quite an oxidizing agent, so it oxidizes, okay, various pathogens and viruses and bacteria. It is used for purifying air in crowded place. Again, the same principle. Okay, again the same reason why actually we use it, because that's what, in a crowded place the air actually get polluted. Okay, obviously not only with other pollutants, but also with pathogens and bacteria and germs. So obviously to kill it, we actually purify it with ozone. Okay, it is used in industry for manufacture of KMNO4, artificial silk, and synthetic camphors. Okay, so these are some of the important applications of ozone. Okay, now finally coming for the oxides. Okay, so what do we mean when we say oxides? Remember that oxide is nothing but a binary compound, okay, of any element, whether it is metal, non-metal, or metalloid, with oxygen. So if any metal or element or any non-metal or metalloid is reacting with oxygen and forming a compound, that particular compound is nothing but known as oxide. Okay, so a binary compound of oxygen with another element, any other element, okay, metal, non-metal, or metalloids, is called oxide. Now oxides are classified basically into 4 types. Okay, based on their acidic and basic characteristics. And the first one, which is basic oxide. So how do we know that an oxide is basic? An oxide is said to be a basic when actually it is reacted with water and it generates a base. Means if you take oxide, react it water, dissolve in water, and if it gives you a base, then it is basic oxide. Now, how to know? Usually, obviously, we'll not be able to demonstrate it. Let's say if or we will not be able to do it practically, right? So if anyone will give you any oxide formula of oxide, then how do you know that, okay, it's a basic oxide? Always remember that metal always forms basic oxide. Like alkali metals, group 1, alkaline earth metals, group 2, transition metals, d block elements. Okay, all this, okay, elements will always, if they are metal, then they will always form basic oxide, like Na2O, MgO. Na2O sodium is group 1, Mg is group 2, Fe2O3, Fe is a transition metal. So all this, okay, metals are nothing but the or these elements are nothing but metal, and they form always basic oxide. Even if you actually take all this oxide and dissolve in water, like sodium oxide, if I dissolve in water, it will give me sodium hydroxide. Magnesium oxide, if I dissolve in water, it will give you magnesium hydroxide. Ferric oxide, if I dissolve in water, it will give me ferric hydroxide. So that is how actually we can prove it also. Then acidic oxide, just the opposite case. Whenever you dissolve any oxide and it gives you an acid, then it is acidic oxide. Then which element will form acidic oxide? Obviously, when metal will form basic, so non-metal will form acidic. You can see carbon dioxide, sulfur dioxide, phosphorus oxide, carbon, sulfur, phosphorus, all are non-metals, okay, and they form the acidic oxide. You can take any of this particular oxide, like phosphorus pentaoxide, you take and dissolve in water, it will give you phosphoric acid. Sulfur dioxide, dissolve in water, it gives you sulfurous acid. Carbon dioxide, dissolve in water, it will give you carbonic acid. Okay, then coming for amphoteric oxide. Now whenever anyone say amphoteric oxide, remember that, like if I take a basic oxide, it will react with acid, right? Obviously, if it is a basic, then it will react with acid. If it is acidic oxide, it will react with a base. Amphoteric oxide reacts with acid as well as base. So if there are oxide which reacts with acid as well as base, then such oxides are usually amphoteric oxide, and they are formed by usually metalloids, okay, the borderline elements like aluminium, tin, Okay, so you can see aluminum oxide, tin oxide. So usually the metalloids tend to form amphoteric oxides. Okay, and finally coming for neutral oxides. So neutral oxides are those which will neither react with acid nor with bases. Okay, so oxide which neither reacts with acid nor with the bases are known as neutral oxide. There are a few specific examples of neutral oxide which you need to remember, like what you have is water, H2O, nitrous oxide, N2O. N2O is nitrous oxide, which is commonly known as laughing gas also. NO, nitric oxide, okay, carbon monoxide. All these are specific examples of the oxides, okay, or neutral oxides. So that is how actually we can understand what are the different oxides, okay. So remember that all this, just a point, all these 4 types of oxide comes in the category of simple oxides, okay. So what are these simple oxides? Simple oxides are nothing but those oxides where that particular element which is forming oxide is in one oxidation state. Like if you take any of these cases, okay, if you try to find out the oxidation state of that particular specific element, metal, non-metal, or metalloid, then you'll find one oxidation state. But there exists some oxide where the element actually exists in 2 different oxidation states. Such type of oxides are known as mixed oxide. Like one such example is Fe3O4. Fe3O4. In Fe3O4, if you see the oxidation state of iron, iron is present in 2 oxidation states, +3 and +4. Actually, Fe3O4 is nothing but a mixture of FeO and Fe2O3. You added this to FeO plus Fe2O3. You added, what you'll get is Fe3O4. In FeO, the oxidation state of iron is +2, and Fe2O3, the oxidation state is +3. So whenever we have 2 simple oxide mixed together to give you another oxide, basically that is mixed. So in mixed oxide, you will have always that particular element in 2 oxidation state. Like other example of mixed oxide is Pb3O4. Okay, when we say Pb3O4, it is a mixture of PbO and Pb2O3. Okay, so these are some of the examples of mixed oxide. So remember that when we say basically basic oxide, acidic oxide, amphoteric, or neutral, it comes in classification of simple oxides. Okay, so that is all about oxide and the oxygen and its compound. Okay, so what we have done in our today's video is we have learned about dioxygen, its preparation, its what do you call it, its properties. Then we have come for ozone preparation and its properties, the uses of oxygen and ozone, and finally we have learned about oxide, the different types of oxide, their examples. Okay, what do you mean by simple and mixed oxide? So that's all for this particular video. Thank you, everyone. Do subscribe for this channel for explanation on various topics in chemistry. Thank you.